Uh, So, good morning, students. Today, today we are discussing paper 6, unit 20. Paper 6, unit 20. Today we are discussing paper 6, unit 20. That is chiral reagent control and catalyst control methods. Chiral reagent control and catalyst control methods. Chiral reagent control and catalyst control methods we are discussing. First one is first we are going to discuss chiral reagent control methods. First we are discussing chiral reagent control methods. Control methods. Chiral reagent control methods. So in this chiral reagent control methods, uh, reduction using chiral aluminum hydrates. First one we are discussing reduction using chiral aluminum hydrates. Reduction using chiral aluminum hydrates. So in this chiral aluminum hydrates, when we take lithium aluminum hydrate is a non-chiral. When this compound reacting with chiral alcohols, when reacting with 3 moles of chiral alcohol, this is chiral alcohol, 3 moles of chiral alcohol, then elimination of 3 moles of hydrogen plus lithium aluminum hydroxy taken 3H. Now it is chiral lithium aluminum hydrate. Chiral lithium aluminum hydrates. Chiral lithium aluminum hydrates. So when we take this chiral lithium aluminum hydrate, we are going to this chiral lithium aluminum hydrate act as a reagent. It is a chiral reagent. It is a chiral reagent. It is a plays an important role in the synthesis of asymmetric synthesis. It's a plays an important role in asymmetric synthesis. So that is I'm discussing here. When we take example, for general example is when we take propione. Sorry, this is a wrong. Phenyl propionone. Okay, this is when this compound phenyl ethyl ketone, when this phenyl ethyl ketone, when reacting with the in presence of chiral reagent. This is a chiral reagent. It's a chiral reagent. It's act as a chiral reagent. When this chiral reagent, lithium aluminum hydrate, then undergo reduction of carbonyl compounds to alcohols. Reaction of carbonyl compounds to alcohols, then alcohol and hydrogen. That that enantiomeric excess, percentage of enantiomeric excess is 90% of enantiomeric excess is the product. Okay, this is 90% of enantiomeric excess is the product. Okay, this is a mechanism. Okay, here next we are going to reduction using chiral alkyl boranes. This is a very important. This is a very important. This is a reduction using chiral alkyl boranes. chiral alkyl boranes. This is a very, very important reduction using chiral alkyl boranes. So when we take boranes are this is an example. When we take, this is the alpha pinene. When alpha pinene reacting with 9-BBN, 9-BBN. This is 9-bicycloboro 331 nonane BBN. 9-bicycloboro 331 nonane is the 9-BBN. Is a organoboron reagent. When this organoboron reagent reacting with alpha pinene, then forms a product that is, then here hydrogen going to here alpha, and here this here hydrogen is beta, that boron going to alpha. So this is a product. It is a IPC BBN. IPC BBN. This IPC means isopynocamphenyl. Isopynocamphenyl BBN. Okay, when this is this act as a chiral reagent. Okay, this is IPC BBN act as a chiral reagent. It gives a direction for the asymmetric synthesis of carbonyl compounds and the reduction. Okay, this gives a direction for asymmetric synthesis of carbonyl compound, reduction of carbonyl compounds. Okay, when we take one example I am taken here. One example. This is deuterated benzaldehyde reacting with the IPC-BBN. Reacting with IPC-BBN. Then the product is deuterium phenyl OH. So the percentage of formation of product is 100% of enantiomeric excess. Only one product will be formation takes place. So mechanism for this reaction is when we take IPC-BBN, hydrogen, boron, IPC-BBN. When this IPC-BBN reacting with phenyl deuterium, okay, so deuterated benzaldehyde. So when we take top, that is so 1, 2, 3. Top phase is rephase. This top phase undergo reduction. So this hydrogen approaches to here. And then therefore this and the boron attacking going to void side. The void side. When then therefore I'm writing here hydrogen going here, and deuterium is top side. Phenyl going to downside. And it is OB2 cyclic. Okay, this is a compound. When this compound under hydrolysis, the bond is broken between oxygen and boron. Then carbon that convert into alcohol. This is 100% of enantiomeric excess product is the formation takes place. Okay, this is a product. Okay, next one is next example. This is a very, very important. By reduction by using chiral alkyl boranes, are very, very important. This is a mechanism involved in the formation of 100% of reduction of carbonyl compound by using chiral reagents, that is IPC-BBN. IPC means isopynocamphenyl BBN. That's a BBN. Bicycloborin 331 nonane is the BBN. Next one is Next one is hydroboration using chiral alkyl boranes. Hydroboration is hydroboration using chiral boranes. Hydroboration using chiral boranes. Same we are taken chiral boranes are then same we are taken IPC BH3 borane. When boron, the boron attacking at the less substituted olefinic carbon, then your hydrogen, this hydrogen going to come front side, your BH2, this is IPC BH2. When we discuss here, when we take is a 1 mole of IPC react alpha pinene reaction. If you take 2 moles of alpha pinene, here 2 moles of alpha pinene, this is IPC taken to BH. IPC taken to BH is the this is chiral boranes. These two are chiral boranes. Chiral boranes. These two are act as a chiral reagent in the synthesis of asymmetric synthesis. Okay, when we take best example for the hydroboration using chiral boranes, when cis 2-butene, when we take cis 2-butene, that is IPC2BH, followed by oxidation, the product is H methyl C2H5. Okay, this is that this gives R2 butanol. R2-butanol is the product. They forms in above the 98% of enantiomer X is the product. Okay, so we are going to discuss mechanism for the reduction of cis-2-butane. So mechanism for this reaction is hydrogen BH IPC hydrogen. In this compound reacting with so here methyl hydrogen, here two methyls. This attack on less hindered transition state will be formation takes place. Less hindered transition states will be formation takes place. Hydrogen here and IPC going to here, then forms. So that product is IPC, boron IPC, C2H5 and C2 and here methyl, here hydrogen. So then under oxidation, the product is OH, hydrogen, here methyl, C2H5. This forms about 98 point enantiomeric excess. Okay. This is a reduction of cis-2-butene. When we take trans-2-butene, for trans-2-butene, we are take IPC-BH2. Just remember, for cis we take IPC2BH, for trans we take IPC-BH2. Then the product is C3H5, C3H7, and here C2H5 and hydrogen. Hydrogen is the product. Okay. For this reaction, when IPC BH2, IPCBH2, when IPCBH2, C2H5, C2H5, hydrogen. When these two compounds undergo less in the transition state formation takes place, hydrogen attacking boron here, less in the transition state formation takes place, then IPC, hydrogen, C2H5 and C3H7. When this compound undergo oxidation, then forms OH, C3H7, C2H5, and here hydrogen. This is forms about 75% of enantiomer cake. Just to remember, for cis tributane, that is IPC2BH, IPC2BH. For trans tributane, IPCBH2 is the alkyl reagent, chiral reagent for the reduction of that alkenes. Okay, just remember, for cis we take IPC2BH, for trans we take IPCBH2. Next, reduction with the Grignard reagent. Reduction with Grignard reagent. Reduction with Grignard. Reduction with Grignard reagent. Reduction with Grignard reagent. When just we take, so we take isopropyl phenyl ketone, reacting with the Grignard reagent, chiral Grignard reagent. We take chiral Grignard reagent, This is a chiral Grignard reagent. Then that product is, then reaction takes place here. Reduction takes place and phenyl isopropyl. Here, this is went to here from less here, that is phenyl isopropyl dot side and hydrogen OH. This is forms about 95% of enantiomer cakes is the product. So for this mechanism here, the mechanism is when we take phenyl alpha and isopropyl, and this compound reacting with hydrogen, ethyl, methyl, magnesium halide. Okay, and this compound here, simply here this is a positive charge and here negative charge. This is involves like this, then forms hydrogen shifting here with ketone migration takes place, then followed by hydrolysis. The product is isopropyl OH, then hydrogen. This is a mechanism for this reaction. That is a Grignard chiral reagent. Next, we are discussing So we're going to asymmetric epoxidation, Jacobs and epoxidation. Actually, in your notes, in your book, that is in Unit 20, 20.20.4 topic is there. That is a chiral catalyst control method. Actually, pages are missing in your book. That is chiral catalyst control method. That is asymmetric epoxidation, Jacobson epoxidation, and asymmetric hydrogen asymmetric hydrogenation using Wilkinson catalyst. And these three topics are missing in your pages, book pages in your notes. So I'm explaining here. Next, we are going to discuss asymmetric epoxidation. There is chiral catalyst control asymmetric synthesis. Chiral catalyst control asymmetric synthesis. We are going to discuss chiral catalyst control asymmetric synthesis. Chiral catalyst control asymmetric synthesis. That is, we are going to discuss asymmetric catalyst control asymmetric catalyst control methods. Asymmetric catalyst control method. In this asymmetric catalyst control method, that is asymmetric epoxidation. There is asymmetric epoxidation. We are discussing asymmetric epoxidation. That is sharpless epoxidation. When we are discussing sharpless epoxidation. In this sharpless epoxidation, we are take isopropyl. There is LL alcohols with LL alcohol reacting with LL alcohol is reacting with hydrogen tertiary butyl hydrogen peroxide and plus DET diethyl tartarate plus DET diethyl tartarate. DCM is a solvent and titanium isopropoxide is a this is a reagent. It is a catalyst. This is a reagent and is a catalyst. Then the forms that is plus DET. We take alpha is the major. Alpha is major. Alpha epoxide major. This forms about the 90% of enantiomeric excess. If you take, I'm explaining here. If you take minus DET, that is beta epoxide is the major. Epoxide is the major. Just to remember here, here, if that condition is for sharpless asymmetric epoxidation, very, very important. This is sharpless asymmetric epoxidation. So that essential needs for the sharpless epoxidation is LL alcohol, tertiary butyl hydrogen peroxide plus DET, diethyl tartarate is the catalyst. DCM solvent, titanium isopropoxide is the reagent. Okay, just remember when we take here, when we take here, just remember if it is LL alcohol for the condition, just for starting material, we take we stand near to a double bond. We are stand near to double bond. The double bond origin is a CH2 methyl group. We are standing here near to origin of double bond, near to origin of double bond, near to origin of double bond. So we see the molecule along the double bond axis. We see the molecule along the double bond axis. If this methyl CH2OH is right side, if CH2OH is right hand side, okay, right hand side, if the CH2OH is right hand side, if that catalyst is plus DET, catalyst is plus DET, the product is alpha epoxide. If it is minus DET, the product is beta epoxide. If molecular orientation is like this, okay, same, standing near to the origin of double bond, see the molecule along the double bond axis. If this CH2OH is left hand side, plus DET is the beta epoxide is the major, minus DET is the alpha epoxide is the major. Alpha epoxide is the major. Just remember that I am sending you notes. In that notes, the clear information is there. But just remember, they're asking in your exam point of view, they give like this. They give one example like this, and gives plus DET so what is the product we are expected. So that is important. Just the concept is important. Okay. So we are standing near to origin of double bond and see the molecule along the double bond axis. If that catalyst is chiral catalyst is plus DET is alpha, minus DET is beta. If we standing near to double bond, if it is CH2OH is left hand side, plus DET is alpha, minus DET is the it is the major products in the formation of epoxides. Next one, we are going to discussing Jacobson epoxidation. Jacobson epoxidation. Jacobson epoxidation. This Jacobson epoxidation. Jacobson epoxidation not available in notes, but I'm sending you notes. Okay. Next one is we are going to Wilkinson asymmetric hydrogenation using Wilkinson catalyst. Asymmetric hydrogenation using Wilkinson's catalyst. Asymmetric hydrogenation using Wilkinson catalyst. Wilkinson catalyst. So Wilkinson catalyst is triphenyl phosphine, rhodium, triphenyl phosphine, and chlorine is triphenyl phosphine. This is a Wilkinson's catalyst. It is not chiral. When we convert into chiral Wilkinson catalyst, that is a phosphorus, here phenyl, here aryl, phenyl, then attached to metal complex. So this is a metal complex. This is a chiral Wilkinson's catalyst. This is a chiral Wilkinson catalyst. It is undergo reduction of double bonds. It's a undergo reduction of double bonds. That is hydrogenation of double bonds. Yeah, I'm taking Z double bond, aryl hydrogen ester, here NH COCH3. Okay, this Z compound, the Z double bond. When this double bond undergo reduction with hydrogen methanol and chiral, this is a chiral Wilkinson's catalyst, chiral Wilkinson catalyst. Then the product is CH2 aryl hydrogen NH2 and carboxylic acid. So they forms about a 90% of enantiomeric excess. The name of this compound is L-DOPA. L-DOPA. This forms about 99%, 90% of enantiomeric excess, the chiral Wilkinson catalyst. Next, we are going to reaction uh, catalyzed by enzymes. Reaction catalyzed by enzymes. So first one is Baker's yeast. First one is Baker's yeast. Baker's yeast. Baker's yeast. When this Baker's yeast reducing of carbonyl compounds by releasing hydride ions. Baker's yeast by releasing carbon by releasing hydride ion on rephase. So we are going to 1, 2, 3. So top phase is a rephase. Hydrogen releasing on top phase. Hydrogen releasing on top phase. Hydrogen here OH. They gives 97% of enantiomeric excess. Okay, this is a Baker's yeast. Next one is oxidation. Next, there is a reduction example. Next one is oxidation. For oxidation, horse liver alcohol dehydrogenation. Horse liver alcohol dehydrogenase enzyme or horse liver alcohol dehydrogenase enzyme undergo oxidation. The double bond is there, undergo oxidation. Then the product is carbonyl OH. This is a product. Okay. So next one is amide formation. Amide formation. In this compound reacting aniline followed by papain, then forms CH2 aryl and NH3O phenyl hydrogen here CONH aryl. This is a examples for reaction catalyzed by enzymes. Okay, so this is in today topics. The important topics are reduction using chiral alkyl borines, and next one is hydroboration of chiral alkenes, and we are going to sharpless oxidation important, and Wilkinson catalyst also important. Okay, thank you, students. Best of luck for your exams. So I'm sending you all the notes to your friends and share that notes. Okay, you can follow that notes. It's enough for your exam point of view. Okay, any doubts, anybody? Important questions means when we discussing topics, I am telling this is important. This is that one is important. మనం ఎప్పుడైతే డిస్కస్ చేసుకున్నామో అవి ఏదైతే ఇంపార్టెంట్ చెప్పానో అది సరిపోతుంది ప్రిపరేషన్ కి.
సార్ గుడ్ మార్నింగ్ సార్.
చెప్పండి.
హలో
చెప్పండి.
సార్ మీరు ఆన్లైన్ లో చెప్పినటువంటి ఇంపార్టెంట్ టాపిక్స్ మేము దాదాపు టిక్ చేసుకున్నాం సార్. ఒకసారి ఆఫ్లైన్ లో మేము అటెండ్ కాలేదు. మేము కొన్ని దూరం ఉండడం వల్ల టీచర్స్ కాబట్టి మాకు ఇబ్బంది ఉంటుందని ఆఫ్లైన్ క్లాసెస్ అన్ని అటెండ్ కాలేదు సార్. కొద్దిగా ఆఫ్లైన్ క్లాసెస్ లో చెప్పిన చాప్టర్ నుండి ఏమైనా ఇంపార్టెంట్ టాపిక్స్ ఉంటే కొద్దిగా మీకు వీలున్నప్పుడు పెడతారేమని రిక్వెస్ట్ సార్, అంతే.
అదే పర్లేదు. యాక్చువల్లీ నేను ఆల్రెడీ మీ క్లాస్మేట్స్ కి నేను చెప్పాను, వాళ్ళు ఒక్కసారి మీరు అడగండి. నేను ఎందుకంటే నాకు మళ్ళీ బుక్ తీసి చూడడం కష్టం. వాళ్ళకి ఆల్రెడీ చెప్పాను, వాళ్ళు నోట్ చేసుకున్నారు. వాళ్ళు అడగని వాళ్ళు చెప్తారు. ఓకే
ఓకే సార్. ఓకే, థ్యాంక్ యూ సార్.
రైట్. ఇంకా నోట్స్ కానీ పంపించాను, చూడండి వాళ్ళకి.
ఓకే సార్. ఓకే.
Any doubts regarding the notes and topics? Okay, thank you, Andy. Thank you very much.